Hey everyone, we today are going to meet regarding section 6.3 or properties of the trigonometric functions. So today we're going to discuss some of the relationships that I've kind of alluded to over the last two videos between some of the functions and some of what are called the fundamental identities. First, before we go into identities, I want to talk about the domains of the trigonometric functions. So first, sine and cosine. If you're thinking about sine of an angle, remember that sine is based on the y value in the unit circle. So if we are in a circle, so if we're talking about y values, no matter where we are on the circle, the y value always exists. So same thing is true with cosine. If we're talking about cosine, we're talking about our x values. And those values can be 0, they can be 1, they can be anywhere between those two, but there's never a time where they don't exist. So if we're referring to the domain, remember in review, domain are the legal values that we can put into a function. If we're talking about the domain of both sine and cosine, we can put any values in there. So those are from negative infinity to infinity, or all real numbers. Now what comes back out of the sine and the cosine function is restricted. So if you look at this unit circle, remember that this point here is the point 1, 0, so cosine gets to 1. This point here is the point negative 1, 0, so cosine gets to negative 1. But all the other points on this unit circle, the x value is between. So if you're talking about the range, cosine is restricted between negative 1 and 1, including those endpoints. Same thing is true as sine. So sine achieves its high value here at 0, 1. Remember, it's our y value. And its lowest value here at 0, negative 1. So sine is always restricted between negative 1 and 1 as well. So the range for both of those is from negative 1 to 1 in interval notation. Now, if you're talking about the tangent function, remember that the tangent function is the y value over the x value. Now, most of the time, the tangent is fine. So if I'm talking about y over x here, I don't have a problem. Y over x here, I don't have a problem. But there are two places on this unit circle where I do. So if we're talking about this line right here, the y-axis, then if we put x in as 0, then we have a problem in this domain. So here x cannot equal 0. Now that means that we cannot have, the tangent function is not defined on the 90-degree lines, or the pi over 2. So it's considered all real numbers except for pi over 2 and integrals of pi after that. So it's all real numbers. I'm going to do this in set notation. Domain is all real numbers except pi over 2 plus k pi over 2. So every additional interval of pi over 2, we also have a problem. So pi over 2 and odd integer multiples of pi over 2 is how they have it phrased here. So I'll phrase it the same way. So odd multiples k pi over 2, where k is an odd integer. Moving to the other functions, if we're talking about cotangent, this one is x over y. So we have a problem in cotangent where y is equal to 0. Now, y is equal to 0 on the pi line, so integer multiples of pi. So all real numbers except k pi, where k is an integer. secant, our secant function is our reciprocal to cosine. So our secant function is equal to x over r. And so we cannot have anywhere where the cosine function is equal to 0. So let's continue to talk about some of the reciprocals. Cosecant is the reciprocal of sine. So remember that sine is y over r, so cosecant is r over y, and r is equal to 1. So wherever y is equal to 0, cosecant cannot exist. So y is equal to 0 on the pi marks. So we have all real numbers except for k pi, where k is an integer. Last one is our secant function. And our secant function is r over x. And that means that x cannot equal 0. So this one follows the same as the tangent. Pi doesn't have 3 legs. Where k is odd. All right, so those are the domains of all the trig functions. And we'll go through over the next couple of weeks how to draw them all. You'll get very familiar with these functions. But for now, here are their domains and ranges. Now, as you were talking about the range for these functions, we didn't go over them expressly. The range for tangent is all real numbers. They're up here in the form here. Cosecant and secant have to be greater than +1 or less than -1, and those are inclusive, so it can be greater than or equal to. And cotangent is also all real numbers. Some of the relationships between the trig functions help us to determine what the trig functions are of bigger angles or in relation to each other. So all of the trig functions are periodic. You can go around the unit circle more and more and more around the circle multiple times. The values repeat after a specific interval. So if you're talking about sine and cosine, these ones repeat after 2 pi. So if we're looking for the exact value of one of those things, then we can put it in the 0 to 2 pi and then use the unit circle. So if I want to find the sine of 17 pi over 4, then I need to put that within the original unit circle and use the unit circle. So 17 pi over 4 pi over 4s, then we have 8 pi over 4 gives me 2, 16 pi over 4 gives me two revolutions of the circle. So let's subtract 2 pi. And subtracting 8 pi over 4 gives me 9 pi over 4. Subtracting 8 pi over 4 again is pi over 4. So when I'm looking for the sine of 17 pi over 4, really I'm looking for the sine of pi over 4. This angle is considered a coterminal angle, so it goes around and meets that same point again. Pi over 4 in our unit circle is this 45-degree angle. Remember that these points, 45 degrees, square root of 2 over 2, square root of 2 over 2. Sine is our y value, so this is the square root of 2 over 2. If I want to find the tangent of 5 pi over 4, 5 pi over 4 is between 0 and 2 pi. Pi over 4, 2 pi over 4, 3 pi over 4, 5 pi, 4 pi over 4, 5 pi over 4. So I'm looking for the tangent of this value. Now, tangent is the slope of the line, and it repeats every pi units instead of every 2 pi. So this is the same as the tangent of pi over 4. Now remember that we can find the tangent by finding the y value and putting it on top of the x value. So these places, square root of 2 over 2, square root of 2 over 2. If I look at that third quadrant, negative square root of 2 over 2, negative square root of 2 over 2. Either way, the tangent of that 5 pi over 4 or the tangent of pi over 4 is equal to the square root of 2 over 2 over square root of 2 over 2, or 1. So the tangent of that is equal to 1. In the video for 6.2, we talked about the signs of sine and cosine for the quadrants. So if I'm talking about all of the trigonometric functions, sine of theta, remember that sine of theta is related to our y value. So wherever y is positive, sine of theta is positive. So y is positive here, here, but negative in the other two quadrants. Cosine of theta is our x value. So wherever x is positive, so is cosine. So we are positive here and here, negative here and here. Tangent of theta is y over x. Here's our y, here's our x. So if we have y over x, that means that tangent is positive wherever y and x are the same sign. So they're both positive here, so that means tangent is positive. In the second quadrant, sine is positive, cosine is negative. So since they're opposite signs, tangent is negative. Third quadrant, they're both negative, making tangent positive, and one of each in the fourth. Cosecant of theta also has to do with sine of theta. So remember that this is y on the bottom. So it doesn't change the sign. So it's positive and positive and negative and negative. Secant of theta matches cosine because it's x. So it's positive and negative, negative and positive. And cotangent of theta, x over y, positive and on the diagonals. So if we have an angle and we know that sine of that angle is greater than 0, then sine of an angle is greater than 0 in these two quadrants. If cosine of theta is less than 0, cosine of theta is less than 0 in these two quadrants. So if we need to know what quadrant theta is in, then it's the only one that matches that description. So theta is in quadrant 2. An identity is a relationship that is between trigonometric functions. So I've been trying not to use some of the identities as we go along, and they're so ingrained as I've been looking at trig for so long, it's hard. So let's teach you some of those identities so we can function easier, because that's what identities are really for. So the first one I wanted to show is that the tangent of theta is equal to sine of theta over cosine of theta. So we've alluded to this a little bit by calling it y over x, but I want to actually show the proof on why this is true. So remember that sine of theta is equal to y over r. Cosine of theta is equal to x over r. And tangent of theta is y over x. So if I plug in y over r and x over r for sine and cosine, what we want to do is simplify that side. So I'm leaving the tangent theta side alone, and I'm replacing sine of theta with y over r and cosine of theta with x over r. Now if I want to simplify a complex fraction, hold the top steady, flip the bottom, and multiply. So here I have y over r multiplied by r over x. My r's cancel, and I get y over x, which is tangent of theta. Check. So that's what we were going for. I wanted to be able to show that sine theta over cosine theta is equal to tangent theta. Now the reciprocal identities are based on the y over r and x over r and y over x relationships. So if you have sine of theta, it is 1 over cosecant of theta. And that's because sine of theta is equal to y over r when cosecant theta is equal to r over y. So 1 over cosine, or 1 over cosecant of theta. Cosine of theta is 1 over secant of theta. Tangent of theta is 1 over cotangent of theta, and the reverses are also true. Now we can use these identities to establish some more identities in the future. So in a few sections we'll get into establishment of trigonometric identities, and you'll see more of these. Some of the other identities that are used very commonly are called the Pythagorean identities. Now these are based on the Pythagorean theorem and knowing some right triangle trigonometry. So let's talk about some trig. If I were to draw a triangle, a right triangle, and this is here in the unit circle. So the length of our hypotenuse is 1. The length of this leg would be cosine of theta. The length of the other leg would be sine of theta. Pythagorean theorem states that a squared plus b squared is equal to c squared in a right triangle. So if I match this up with this right triangle that's in the unit circle, then A and B are your legs and C is the hypotenuse. So here we have cosine of theta squared and sine of theta squared. The order doesn't matter, is equal to 1 squared. Now when you square a trigonometric function, we typically put the square mark in between the cosine and its angle. So a cosine can't just be written cos, C-O-S. It always has to be taking cosine of something. That's its variable there, or its angle. So we put the 2 from the square on the inside so that you don't confuse whether the cosine is squared or whether the angle is squared. So I'm going to change the order because it looks like this. So sine squared theta plus cosine squared theta is equal to 1 based on our Pythagorean identity. Now we can also show the other Pythagorean identities using this one. So 1 plus cotangent squared theta is equal to cosecant squared theta. We can take our original one and divide through by sine squared. So if I have sine squared theta plus cosine squared theta equal to 1, and I divide everything, remember you can divide legally as long as you do it all the way across, by sine squared theta, and then use some of my relationships we learned above. Sine squared over sine squared is equal to 1. Cosine squared over sine squared. Looking at my identities, sine squared over cosine squared is tangent, but cotangent is 1 over tangent. So I can say that this is cotangent squared theta. And then 1 over sine is cosecant squared theta. Similarly, if I divide the original through by cosine, what I get is this relationship. 1 plus tangent squared theta is equal to secant squared theta. So even odd identities are based on our reflections across the quadrants. So if I'm looking at a sine value and I change its argument, its angle from positive to negative, say we started with this angle and we have this value of y. If I reflect this angle in the negative direction, same angle, but my y value is the same but negative. So if I put a negative sign in with the argument for sine, my negative sign stays and comes out to the front. Versus cosine, if we have an angle, remember cosine's our x value. So here's our x value for this angle. If I make the same angle negative, that x value is the same. So if we've got a negative in with the argument, we can eliminate the negative using reflections. Tangent is based on sine. So anything that has sine involved keeps its negative sign. Cosecant is based on sine. Has sine involved, keeps its negative sign. Secant is based on just cosine, so it does not have a sine involved, so it loses that negative sign. Cotangent also has a sine involved, so it keeps its negative. Now I can use that to find some values of some trig functions. So sine of negative pi over 3 is equal to the negative of sine of pi over 3. Now pi over 3 is this angle here. So my y value is high, and this is negative square root of 3 over 2 based on the unit circle. Most of the time, this allows us to bring most of the angles for the whole unit circle into that first quadrant, so I don't have to remember as many angles. So cosine of negative pi over 3 by the even-odd property is equal to the cosine of pi over 3. And that same angle says that cosine of pi over 3 is equal to a half. All right, this has been quite a bit of information today, so if you have any questions or concerns, please reach out. I'm happy to make a time to meet with you for conference, or I have office hours that are posted that are drop-in time. Have a good day and get started on your homework. Thanks.